Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series on applied electronics. We have been going through a series of lectures in the paper Basic Physics 2, and the syllabus goes as follows. You have got defects of images, about which we discussed in a greater detail, and we now pass on to the next and a very important section, namely the phenomenon of interference. We will be discussing about interference as a lecture number 10, the contents or the nature of light radiation, interference, characteristics of waves, transverse and longitudinal waves, constructive and destructive interference. Let me now ask you straight away. We are in a room here sitting under illuminated lamps. You have got light, we are seeing the light radiation. Let me ask you, the youngsters like you, whether light travels in the form of rays or waves or corpuscles, or whether light is made up of particles or waves, or they traveling in straight lines. Okay, you have got so many questions, right. Now, it was Newton who talked about light in a greater detail. According to Newton, light travels in straight lines, and then he also assumed that light is made up of corpuscles. So, when light radiation is coming from the source to the eye, so light travels in the form of rays. This is what Newton thought, because you get images for the object that you have got here, you get the image. I have got object here, when light is there, I get my finger is the object, and light that is coming here, it gives rise to image on the screen, that is my other hand. So, light obviously should travel in the form of straight line, that is what Newton said, and also he assumed that light consists of particles or packets of energy, which he called as corpuscles, and so he laid down what is called the corpuscular theory of light. Then came one Christian Huygens, who said light should be traveling in the form of waves. But who is correct, whether Newton, who said light travels in the form of rays, whether light is traveling in the form of rays or waves, right? You got light wave, which one is right? Now, the experimental proof came from Thomas Young in the year 1801. In 1801, Thomas Young was able to offer some very strong evidence to support what is called the wave model of light, the wave theory. So, the wave theory came into existence. Do not ask me at this point of time whether light is a wave or it is made up of particles, right. Now, you should be able to answer at a later date, or by now you should be knowing the answer to the question whether light consists of particles or light is made up of waves. Okay. As of now, if you want to explain the phenomenon of interference, I will tell you later what is meant by interference. So, I am going to discuss about a series of new phenomena such as interference, diffraction and polarization. You would have heard of X-ray diffraction. So, these phenomena of interference, diffraction, polarization can be explained only by assuming light coming from a source, whether it is the ordinary light or X-rays or gamma rays, the entire electromagnetic spectrum. The light is made up of waves. So, you have to make use of wave theory. So, we talk of wave theory of light. So, in the year 1801, when Thomas Young gave the experimental proof that light is made up of waves, he placed a screen in front of two slits. You have got a screen here, you have got two slits illuminated by light here. The light that is coming through the slits will give rise to what is called an interference pattern, that one can understand the interference pattern, which I will be showing later, only on the basis of what is called a wave theory. What is wave theory? That is, light is made up of waves. Okay. Now, I am showing you the galaxy of important scientists who made us to understand the nature of light. So, they are the pioneers in the visible light physics, because you see, you cannot see X-rays. Why can't you see X-rays? What will happen if you try to see X-rays or gamma rays? Your eyes will be blind if you use gamma rays or X-rays to, you cannot see those rays, because the visible region only the human eye can see, starting from 7,000 angstroms, and we are talking about the visible light, because that is the light that you can see when you place a prism and make the white light to be incident, you get all the colors and order of Vibgyor. And so, we are confined, we are concerned only the visible region extending from violet to red. Okay. So, it was Isaac Newton who gave what is called a corpuscular theory of light, right. He lived from the year 1642 to 1727. So, more or less Huygens was his contemporary, who lived from 1629 to 1695. He died much before Newton passed away, but it is Christian Huygens from Netherlands. He gave, or he proposed, the wave theory of light. So, in the years from 1695 or 1720, after 1727 also, people could not find out whether light is made up of rays of light, or whether the corpuscular theory is correct, or the wave theory which was propounded by Huygens, whether which theory is right. I told you 1801 that he lived from 1773 to 1829. So, during 1801 he performed the so called Young's double slit experiment. I will discuss the double slit experiment a short while, and in 1801 he showed conclusively that the wave theory propounded by Christian Huygens is correct, in the sense that if you want to explain interference, the phenomenon of interference, then you have to accept the wave theory of light. Light is a wave, light travels in the form of waves. Okay. If you assume light to be traveling in light rays or made up of corpuscles, particles of packets of energy, then you cannot explain the phenomenon of interference. What is meant by interference could be understood only if you know more about waves, the characteristics of waves and so on, right. What is meant by wave? What kind of waves are there? Okay. These things we have to see at the beginning, and now I have this picture. What does it show? It is written below the picture, a stone is dropped in a pool of water. You drop a stone, you got a pool of water, you drop a stone. So, you produce a disturbance and then you see nice waves being generated, right. The waves, you got a disturbance. So, the wave is generated and again wave will be moving, and so the light waves will be going. Okay. So, the light wave, the medium is disturbed, the water medium is disturbed and you see the waves, right. Okay. And so, the water particle goes up, it is called a crust, and then it comes down, it is called a trough. And so, you have the alternately you got a crust and then a trough and then a crust and then a trough and so on. So, you see a crust here, right. You see a crust and then a trough here, see a crust here, trough here. So, the disturbance is propagated from the point where the disturbance is produced and it ends there, right. Slowly it gets damped. If you drop a stone in a pool of water, the disturbance will be large and then slowly it disappears, right. It slowly disappears. Not only one stone, initially to explain or to make you to understand the important terms, the terminologies like amplitude, wavelength and so on. I am showing this picture wherein I am using only one small stone being dropped. I am going to drop two stones later. I will tell you why I am dropping 2 stones. Okay. That will come later. So, you generate a wave. Okay. Now, the water particles move up and down. Okay. When you drop a stone, the disturbance is caused on the medium, the water medium is getting disturbed and the water particles move up and down. The wave is travelling in this direction, right. From the point of disturbance, the wave is moving from here to there or from here to. So, in this direction, in all directions. Okay. The wave is going. So, here wave is going. Okay. So, the water particles, the particles they move up and down. So, the water particles move up and down, the wave is travelling in this direction, right. So, the wave is travelling in a direction perpendicular to the direction in which the particles are disturbed. The particles will move up and down, the wave will be travelling in a perpendicular direction. Now, this wave is an example of a transverse wave, an example of a transverse wave. You take a string, you make the string to vibrate, right. You can produce, as I will be showing in the picture, a lady will be holding one hand with a long string, the other is tied at the other end. So, you make the string to vibrate. Now, when the string is vibrated, you have a wave getting propagated, wave will be moving and the string will be going up and down, right. At every point of a string will be moving up and down. Similarly, every particle of water will be moving up and down, the wave will be travelling in a perpendicular direction. So, if this is the thing, it is called a transverse wave. So, what is a transverse wave? If the particles of the medium which are disturbed, if they are vibrating perpendicular to the direction of propagation, the wave is travelling in this direction, the particles are vibrating in this direction. So, this is how you define a transverse wave. Okay. This is what is happening when a small stone is dropped in a pool of water and the light wave comes under this category. Or you go to the beach, you see the waves coming, right. The waves are transverse waves. So, the waves which are produced on the surface of water is a transverse wave. Similarly, light wave is a transverse wave. But how can you show that the light wave is by seeing the wave, by seeing the radiation? I do not know whether it is travelling in the form of rays or does it contain corpuscles or do you see waves here? In the case of string, you can see the motion of wave that is generated in the sea or in a pool of water. The water particles are going up and down. This can be seen by the human eye. There are indirect evidences that show that the light wave is a transverse wave. On the other hand, what I would like to tell you is a sound wave. I am talking now, the person here is able to hear what I talk, right. The people here, they are able to record what I am talking. Now, these waves, the sound waves are examples of longitudinal waves. In a short while, I will show how the sound wave or the sound that I am making reaches the ears of the persons who are sitting here. The propagation of sound waves, the sound wave is an example of a longitudinal wave. Okay. Light wave is the example of a transverse wave. You know by now what is a transverse wave, then how you can understand the longitudinal wave. What is the difference between a transverse wave and a longitudinal wave, that you should see. A wave may be defined as a periodic disturbance in a medium that carries energy from one point to another. I told you that the energy transfer. When I am talking, supposing the whole room is evacuated, will you be able to hear? I am asking you the question, will you be able to hear what I am talking if there is no air here? If the whole room is evacuated, if there is no air, then you cannot hear. I will, you see my mouth getting opened and closed, but you won't hear anything, right. It will be like films which are shot when maybe several decades back, there is no voice will be coming, right, only the motion pictures. So, likewise I will be only moving my lips up and down, right. So, you will see me doing something, but you won't hear anything, because you need a medium which will carry the sound waves from my mouth to your ears. So, what is the medium? Air is the medium. So, without air, sound will not be getting propagated, right. Sound propagation requires a medium, namely air. Air is the medium which carries the sound wave from the person who talks to the person who hears, right. So, waves may lose energy as they propagate through a dense medium. They get attenuated, as I told you, when you drop a stone also, after some time it will be, the energy gets dissipated or attenuated and the wave dies. Okay. Now, waves that radiate isotropically, isotrope means uniformly in all directions from a source, may lose intensity after some distance. The inverse square law also holds good. So, the intensity of the wave is proportional to the displacement square. I will tell you about displacement, amplitude and other things. A vibrating string is an example. There are two kinds of waves, that is, one is the transverse wave and the other is the longitudinal wave. I told you light wave is the best example for the transverse wave, whereas sound wave is the best example of a longitudinal wave. Okay. There are two distinct types of waves, longitudinal and transverse. Sound waves are an example of longitudinal waves, while electromagnetic waves such as light waves, infrared, ultraviolet, X radiation, gamma radiation, radio waves, they all form part of the electromagnetic spectrum, as all of you know. Now, all these radiations, they come under the character, the class, the transverse waves. Okay. The transverse waves transfer energy in a direction, this is a very important sentence. The transverse waves transfer energy in a direction perpendicular to the direction of disturbance of the medium. In a transverse wave, the particles will be moving up and down, the wave will be travelling in this direction. But what about a longitudinal wave? That you will see now. A vibrating string is again an example of a transverse wave. Although all points of the string itself are constrained to move only up and down, wave pulses move perpendicular to the length of the string. When you generate a wave along the length of the string, every point on the string will be moving up and down, but the wave will be travelling in this direction. The wave speed is the speed with which the pulse moves along the string. A transverse wave may consist of more than one pulse. Transverse waves are produced by disturbances. A series of waves that you get is called a wave train. Now, here is a picture where it shows a person standing here. What she is doing is, she is making the string to vibrate. One end is attached to a stand, you have got a string here, she is making the string to vibrate. Then you see a wave getting transferred, the propagation of wave, but the you know the length of the string is fixed. Only the string at every point will move up and down, but the wave will be traveling in this direction. Remember, the wave is traveling in this direction. The first, the crest here, another crest, the second wave is getting generated. So, the string will be vibrating up and down. The wave is traveling in this direction. This is a characteristic feature of the, or this is how you define the transverse wave. That understood? The particle in the water medium or the string will be getting vibrated in this direction, but the wave will be traveling in this direction. Okay? This is the transverse wave. The longitudinal waves or waves, when I am talking, you got air here, I am sending sound waves, I am talking, right. So, the sound, the energy which I am spreading now, it compresses the air molecules. Okay? The air molecules are getting compressed, and the compression will again expand and again lead to another compression and so on. So, you talk of what you call condensation and rarefaction. Longitudinal waves are waves that transfer energy in the same direction. The energy will be traveling in the same direction, wave also will be moving in the same direction. The longitudinal wave is one in which the air particles or air molecules will be moving in this direction. The wave also will be moving in this direction. But whereas, in the case of light waves or in the case of water or in the case of string, the water particles are moving in this direction. The wave is traveling in this direction. Okay? The wave is traveling perpendicular to the direction in which the water particles are moving. But whereas, the sound wave, the air is responsible for the propagation. Without air, you will not be hearing, right. So, the air molecule will be vibrating in this direction. Okay. The air molecule will be vibrating in this direction. Your wave also will move in this direction. So, both the wave and the air molecules, they travel in the same direction. Okay. The one thing is transverse is this thing, right. So, a longitudinal is this thing, right. The air molecules will be moving up and down. The wave is, so the air molecule will be moving up and down. Okay, up and down in the sense. So, between from back and forth, okay, in this direction. The wave will be moving in this direction again. Both of them will be moving in the same direction. Okay, unlike the case of the transverse waves. Now, you will see now, because of this, the air molecules are made to move, it will lead to compression and then rarefaction, compression, rarefaction and so on. All longitudinal waves consist of regions with high density, a low density. High density is called the compression. The low density means rarefaction. The rarefied means lesser number of molecules will be there. The known as condensation and rarefaction. So, the compression or condensation rarefactions that oscillate around the local positions of equilibrium. The longitudinal wave is the following. What do you observe now? A longitudinal wave is propagated in this direction. You see here a compression. A compression means you got number of molecules here, air molecules here, a clustering, a compression, right. So, here you have got what you call rarefaction. Here it is called condensation. Condensation, you have got more number of molecules found in a smaller region from here to here, is called condensation. High pressure is generated, or as I told you, high pressure means high density of air molecule will be there in the region where you have got what is called condensation. Whereas, this will be rarefaction. This region is called rarefaction, wherein the pressure will be low. Here the pressure will be high, here the pressure will be low. It is a low pressure region. So, the disturbance that is caused will be in this direction, right. The wave will be traveling in this direction, the disturbance will be again in the same direction, and areas of high pressure correspond to condensed regions of lower molecular displacement antinodes. So, the point is the following. So, you have got a region called condensation, where you have got more number of molecules, right, a compressed gas. Here they are rarefied gas, that means lesser number of molecules. So, you have when I talk, I send sound energy, that will make molecules to get compressed, and then the energy will be dissipated, then there will be what is called rarefaction. That from rarefaction again you will have condensation, rarefaction and so on. So, alternately you have condensation and rarefaction will occur. So, a longitudinal wave So, the speaker is here, I am sitting here, you are somewhere here, right. The cameraman is here, I am sitting here as a speaker. Okay. So, the sound wave is getting propagated this direction. In a longitudinal waveform, the disturbance in the air medium is getting propagated this direction, okay, in this direction. This is called a wavelength lambda between one low pressure region, or I call a rarefaction, to another low pressure region rarefaction, or one compression to another compression, that is also wavelength, right. And let me now try to summarize the talk, and the summary goes as follows. According to Newton, light consisted of particles called corpuscles, and he advanced what is called a corpuscular theory. As I told you earlier, it was Huygens who propounded the wave theory of light. It has led ultimately to Young, who performed the double slit experiment, which showed in a conclusive manner that light radiation should be treated as waves and not particles. The corpuscular theory of Newton is wrong, only the wave theory is correct. In what sense? To explain a phenomenon called interference, which is exhibited by light sources. This phenomenon of interference, diffraction, polarization, these phenomena can be explained only on the basis of the wave theory of light. Then the light waves are transverse waves, sound waves, as I told you, are longitudinal waves. Let me now pass on to the question session. Question number 1: what are transverse and longitudinal waves? If a stone is dropped in a pool of water, what kind of waves generated? What is important characteristics of waves? With this, we come to the end of lecture number 10, wherein we saw the beginnings of wave theory of light. In the next lectures to come, we will see the phenomenon of interference. Thank you.